My name is Jeff Fair. I have a PhD in Material Science and Engineering from the University of Minnesota. I have a BA in Physics from Brigham Young University. I've worked with solid-state reactions. I've worked characterizing materials, semiconductor materials, thin films. I currently do a lot of work with nanoparticles as well as solid-state reactions. The way I got involved in 9/11 research was about in 2005. I had read Steve Jones' paper on, his initial paper on why the buildings collapsed that day. To give you a little background, on the day of 9/11, on September 11th, I was actually in Albuquerque waiting to, I had an appointment at Sandia National Lab, which is part of Kirtland Air Force Base. And that morning, a colleague of mine knocked on the door and said, as I was getting ready, he said, a plane just flew into one of the Trade Center towers. And I thought, that's strange. And continued to get ready for our appointment. A little while later, he came back and said, a second plane flew into the towers. And then I thought, okay, this is not just your ordinary news day. Something's going on. So I went out to the lobby of the hotel, and people were watching the news. We all watched what happened. Obviously, the base, Sandia is part of Kirtland Air Force Base, so we knew that we weren't going to be getting on the base that day, and sure enough, the base had locked down. No civilians were going in. So we got a car and drove back to Salt Lake City. So the news of the remainder of that day is a little hazy for me because I wasn't sitting in front of the TV watching the news. And I wasn't aware of Building 7 until I read a Steve Jones paper in 2005, which talks about Building 7, talks about the strange details and evidences of, surrounding Building 7. And that's what really grabbed my attention and made me want to look more into this. And so I actually looked for Steve Jones, and I sought him out, and we talked for a little bit. I wanted to get a feel for his sincerity and his motivation for doing this, and so we talked a little bit, and then I watched one of his talks that he gave in September of 2005 at Brigham Young University. And we talked some more, and at that time I was working as an electron microscopist. I was characterizing materials, and I thought that I might have something to offer if eventually he was to come across some evidence, or evidence was sent to him. And so I offered what I could do to study that and to get some data on any of the evidence that he might collect. So eventually, he was able to get some metal samples that were from some of the steel beams from one of the towers, and we studied those. I cut up some of those steel samples and polished them to see what we would find in the steel. Some of the pieces that he acquired at the time had some corrosion. They'd obviously gone through some melting, and we thought that those might be significant. So we actually were looking, and I was going in that direction. That's sort of my expertise, solid-state reactions, and that's not quite solid-state necessarily, but that's certainly in the realm of my expertise. So that's the direction that I wanted to go, was to look at these materials, study the phases, and maybe see what temperatures that these phases would have to, or the temperatures that the steel would have to get to create these phases. And then around 2006, I believe it was, Steve started receiving dust samples and started looking at these dust samples. So the study of the metal samples turned up different phases. I did obviously see the steel phase and iron oxide phases. We did find an iron sulfide phase as well as an iron silicate phase. looking at all the phases, I came to the conclusion that in order to create these phases, we'd have to reach a minimum of about 1100 degrees C. So that was some preliminary work that we did with these steel samples or the steel evidence that Steve was able to get from various people. In fact, one of the samples came from Clarkson University. Some of the steel beams had been sent out to Clarkson College, and they were going to build a monument with these, and there was a lot of debris that was sent with the beams, and some of that evidence came from that debris as well as coming directly off of the steel columns. So that's where these initial samples came from. Obviously, it required polishing these pieces of steel and then putting them in the electron microscope to find, and using X-ray analysis to find the chemistry. I used diffraction to determine the phase or the structure of the phases along with the chemistry. And then in that way, we were able to determine the phases that were in the steel or in these pieces of steel that had been corroded or melted, whatever the process they had gone through. That's what we were trying to determine by looking at the phases. So again, we found that the phases that were there probably would require about 1100 degrees C. And that didn't entirely wrap up that part of the study, but that was pretty significant findings. The question became, how do you get to those temperatures? Obviously, the question of how do you get to 1100 degrees C is significant because you don't get to those temperatures with scattered office fires or even jet fuel-fed office fires. You get to maybe half that temperature. So that question of how do we get to 1100 degrees C, that became fairly important to me, and one of the things that obviously made me more motivated to look further into this. I don't know that I could really speculate as to. I mean, there's any number of sources of heat that could create that temperature, but certainly not jet fuel burning in open air in an office. I guess what makes these findings significant is. Well, it's sort of the manner in which we found them, the way that the morphology, in other words, of the grains of these phases. You don't get these phases with an oxyacetylene torch or whatever torch you use to cut the steel. You don't get these phases existing together the way that we found them. So it's I don't know. I mean, yeah, people might say, well, they cut up the steel, couldn't you create phases with a torch? Yeah, you probably could. I'm not going to deny that. I mean, that's, and if that's what, if that ends that investigation, then I think what has to happen is you have to be able to take a torch and show that you can create these phases. And so far, nobody's done that. So I don't know. I'm not going to say that you can't do that. We did find small amounts of aluminum in some of the specimens. More significant probably was the sulfur content that we found. In fact, in one piece, I found a pore in the steel that had pure sulfur embedded in the pore, which I thought was very strange. And so that's when I really started looking for sulfur and finding it in more abundance in some of these phases. So then, of course, the next question is how do you get the sulfur in these pieces of steel or in the debris? And that question is unanswered. There are possibilities for sulfur. I mean, any number of possibilities. There's a version of thermite called thermate, which has sulfur in the thermate and what the sulfur does is it's sort of like salt on ice. It creates a eutectic temperature, so it lowers the melting point of steel. and in that way it can cut through the thermate can cut through the steel or melt the steel more quickly than regular thermite. The finding of aluminum in these steel samples, or what used to be steel samples, also supports the theory that thermite was used to melt the steel. I would certainly love to get an official sample of the steel that we know came from a large piece of the steel. This was actually done by Jonathan Barnett. He was contracted with FEMA or by FEMA to do this, and he actually took some of the steel members and cut them up, and he selected some very significant pieces of steel. He found ones that had oxidation or sulfidization of the steel members. Some of them looked like they'd been vaporized, certainly melted, and he cut up portions of that steel at that point, or at the locations where he saw the sulfidization. And he found similar things. He found iron sulfide in one phase. He found that the sulfur phases, or the phases rich in sulfur, were attacking the grain boundaries of the steel, which is exactly what thermate would do. It would go into the grain boundaries first to attack the steel and then melt the steel as it did that, and create that eutectic temperature. His findings were significant in that he originally started with steel from Building 7, and his question was then, do we find the same things happening in steel from Buildings 1 and 2, Towers 1 and 2? And the answer to that was yes, they found very similar things to what they found in the steel of Building 7. And then the next question was, how much sulfur do you need to create these sulfur phases? He did some preliminary tests, and I think those were significant. And those are some tests that if I had the means, if I had the steel and the time, I would do these. I would like to do these tests. How much sulfur do you really need to create these sulfide phases, or these sulfur-rich phases? Some people have speculated that the sulfur could have been supplied by the wall board or the gypsum board that was present in the buildings. And I believe that's calcium sulfate, so it is a sulfate-rich phase. However, in order for that to happen, in order for you to get sulfur out of the wall board, you've got to heat up the gypsum board to high enough temperatures to dissociate the calcium from the sulfur. And then you'd have free sulfur and be able to, and then the sulfur could then attack the steel, attack the iron phase or the steel, and create these sulfide phases which go into the grain boundaries. But again, you've got to get extremely high temperatures to dissociate those two things. And then you'd have the temperature, and then certainly if you've got those temperatures, you've got the temperature to melt the steel. So this would require high temperatures, certainly higher temperatures than you get in normal office fires. So this is impossible to achieve in a normal office fire, even a jet fuel fed office fire. You wouldn't achieve the temperatures required to dissociate the calcium and the sulfur in order for the sulfur to then attack the grain boundaries of the steel and melt the steel.